You paddler, Dr. Gordon Bromley. Pete and I are taking part in the Kandusky race tomorrow, so I think that's hope, right? Who knows or who knew that Scotland looks as good as this? Right. It's not just a land of driving rain and sheep and savage natives. It is a
Whiskey.
It's you don't like whiskey, Dan. It's a rich geologic archive of abrupt climate change, abrupt climate variability in the North Atlantic region. And so that's the context in which I'm going to be discussing it now. Over the last few years, I have become increasingly interested in the problem of North Atlantic stadials and the impact of these events on terrestrial cryosphere and adjacent land masses. That's right. If anyone is not now familiar with the term stadial, then shame on you. You weren't here last night for Aaron's talk. But just to recap, a stadial is an abrupt, short-lived climatic perturbation which involves shutdown or slowdown of Atlantic meridional overturning circulation, expansive sea ice in the North Atlantic during the wintertime, and it has on-land repercussions as well. So ecologic change, and also, certainly in the North Atlantic region, widely believed to force glacier advance, glacial growth. As you'll remember from last night, that's not necessarily the case throughout the rest of the world, but that is the paradigm for the North Atlantic region. Now, the problem that I'm addressing is this: that in recent years, emerging marine data have shown that, or suggest rather, that Heinrich stadials, shown here in blue as periods of mean annual temperature depression in the Atlantic, that Heinrich stadials are also that they coincide with periods of increased meltwater discharge into the North Atlantic Ocean via this. Today it's the English Channel, but during the end of the last ice age, it was a conduit for meltwater from the European ice masses. And so if we take glaciers and ice sheets as a proxy for temperature, the summertime temperature, which governs mass balance of these masses, that would suggest that these ice masses are melting, right? The summer temperature is rising during these periods I picked out in blue, during these periods of depressed mean annual temperature, mean annual sea surface temperature. So that begs the question, what is driving this apparent disparity? And one possibility is, which was presented by George Denton in 2005, is that this reflects seasonality, or extreme seasonality, whereby stadials are characterized in the North Atlantic basin by very cold winter conditions, extremely cold, but relatively mild summers. And I would go so far as to say that this data from Europe would suggest that the summers were warming, not just mild, but were actively warming. So that's a bit of a, well, it's rather a delicious story, isn't it? It's a problem. So that's a problem I'm addressing with surface exposure dating in the Northern British Isles. What I'm doing is I'm reconstructing the changes in ice sheet and glacier extent in the British Isles during the end of the last ice age, during that termination period. That was a period with two Heinrich stadials, 1 and 0. And as you can see here, Scotland, where I'm working, is located in the North Atlantic Ocean. So it's very sensitive to Atlantic climate. This is a very quick story of glaciation in Scotland as we know it. During the last glacial maximum, the ice sheet covered the country, covered most of the UK, and advanced out to the continental shelf, just like in Maine. That's shown by this white line here. Afterwards, it retreated all the way back into the Grampian Mountains. Who knows, maybe it even disappeared. We don't know that. This retreat was punctuated or was followed by a short-lived regrowth of small glaciers in this West Highland ice field. That's during something known as the Loch Lomond readvance during the late glacial, and then everything disappeared. Okay, that's what we know based on geomorphology. What I want to know is when exactly did this major retreat of the ice sheet happen? When did this Loch Lomond advance take place? And then when did the final deglaciation of Scotland after that advance And then how does this pattern, which I equate with summertime temperature, how does that relate to stadials? I'm working at a spot called Anchalik. This is in northwestern Scotland. It's an ideal location for this because during the last glacial maximum, as you can see, it was buried by this ice sheet, went right over the top of these summits, and then it was deglaciated, and then during the Lachlan advance, you can't see it on this map, but it was occupied by small cirque glaciers. So we get the whole story here. This work is very much a pilot data set. It's funded by a faculty research fund from the University of Maine. Strongly recommend people apply for that because it's a great pot of money. And the data that I'm going to show you now were prepared and run at our University of Maine Beryllium Lab. So we're very proud about that. This is looking into a cirque on Anchalik, on that beautiful serrated sandstone mountain. The cirque, hopefully you can see this, is a beautiful moraine here. Let me point it out for you. Okay, that marks the extent of the cirque glacier during the Lachlan advance. Immediately outside is striated bedrock that was it was molded by the ice sheet. Okay, the ice sheet that went way offland. And so for this first view of what was going on here, I sampled boulders immediately outside this late glacial advance to see when the ice sheet had pulled back to this position, and then I sampled boulders on and within this re-advance limit. And I did this, by the way, with the unsinkable Kurt Rademacher, who many of you will remember. I direct work, and Kurt just goes and basically chops the tops off the boulders, lugs all the material down the mountain, and never complains. Never. And so these are 5 ages. These are my first 5 ages from this site, from outside of this limit. And they show that this was deglaciated by, I know you can't read this, it'll say about 15,000 years ago. All right, so this was ice-free by 15,000 years ago. The former center of the British ice sheet was ice-free by then. This is Kurt sampling in typical conditions. This moraine complex, we have 13 ages so far, and they give a peak age of 13,100 years. All right. Again, this is a work in progress. We have more data to come. The final bit of this story then is when did this late glacial ice mass, this regrowth, if you like, when did that come to an end? When was that gone? And I know I'm skipping ahead very quickly here, but I think it was just last week maybe, or the week before, Aaron was very excited because he and I have been working on this for a while. And he just finished a beryllium data set from the former center of the West Highland ice field. All right, so this is the smaller, the advanced ice field. This is a beryllium data set taken from a moraine which dams bogs, which I have radiocarbon dated. Okay, so we have radiocarbon dates and beryllium dates from the same site. And that tells us when, basically, when Rannoch Moor was ice-free, that ice field was gone. The late glacial event had come to an end, and ice was gone from Scotland. There's Rannoch Moor. Never looks like that, by the way. Okay, and this is what we get. So this is Aaron's data set of beryllium. It gives a peak age at 12,300 years ago. Okay, so that's when this moor was deglaciated, or the last moraine was deposited there. This is my radiocarbon data set from the bogs on either side. This tells us when the first vegetation was growing on the landscape after the ice. That gives we have here a conservative date. That's based on the oldest replicable ages, so 4 ages there, of 12,300 years ago. Okay, so that's in close agreement. This is how it looks, plotted on this. This is the Greenland mean annual air temperature. Heinrich Stadial 1, Heinrich Stadial 0, which coincides with the Dryas chronozone, the pollen record. And this is the Berling Allerud here. The 5 ages from outside the moraine, the 5 ages that tell us when the ice sheet is gone, this curve here. In blue, those are from that late glacial advance of ice in the Cirque Glacier, tells us when that won't happen. And then finally, this is when that late glacial event was over and the ice was gone in this curve over here. Now, I'll stress here that this is a work in progress, very much so. Just begun, really. And there's a lot more to do. We have to replicate our findings. Of course we do. Otherwise, this could just be a fluke. And this data set needs to be and will become a lot bigger before we can tell exactly what's going on. But it's compelling. Okay, it's compelling to me to see that a site within the North Atlantic Ocean shows that the ice sheet had gone from its maximum around 20,000 years ago out on the continental shelf. It virtually disappeared within this time period. That the re-advance of ice, the regrowth, think about it, conditions conducive for glaciation occurred not here, but it looks like end of the Alarud or very beginning of the Younger Dryas, and that event was over, done right in the middle of high interstadial zero. It's a compelling picture, and this is the kind of stuff we can do now with our Beryllium 10 cosmogenic lab right here. All right, and as I said, funded by faculty research grant, and also a little bit of money from the School of Earth and Climate Sciences, made possible by actually Scottish Land and Estates, who got me in touch with the people who own this land, who turn out to be millionaires with a very fine wine collection, and invite me to stay at Dundonald House whenever I'm in the city. All right, that's how science should be done. Any questions? Apart from Gordon? Yes.
Yeah, so as one of the savage natives who was born on...
No, I thought that's why you left.
So, we at the school in Scotland, so we're familiar with the history, and there's been a lot of work on Lochlan and re-advanced by systems and Malachite and all these other workers. So how do your new results stack up against what is already known about the glaciers as well?
Most of that work is exquisitely detailed geomorphic mapping, okay, which has shown us exactly where this ice formed, exactly how it retreated, active recession leaving suites of moraines going in valleys, and the nature of the glaciers as well. They look at very close sedimentological structures. One thing that has not ever been, at least to my mind, conclusively shown is exactly when it happened. If you look back in the literature, the first radiocarbon dates agree with our radiocarbon dates that suggest that the Loch Lomond advance, it happened, and then the deglaciation occurred, and that was done early on. Okay, people have said this was an Alarud age advance. And that's just what the data showed. Of course, they were radiocarbon dates, they were bulk from the 60s and 70s and 80s, and so it was wondered what the reliability of that is. But since then, it has been assumed that the Younger Dryas was simply uniformly cold, and that this happened during that time period. And I'm not claiming to have the answer at all. Okay, we're trying to improve the chronology, but we are also the first to address the chronology in a precise manner, in a sort of, without bias. Just let's go and find out when this glacier event happened, instead of saying, well, of course it happened here because it was cold. And so, long story short, they hate this work, actually.
Thank you, Gordon. Our next presenter is Andrea Nurse, who's going to be talking about a new technique to monitor airborne pollen.
Whoops. Okay, what did I do?
Turned it off.
Yeah. Ivan and Esperanza and I, along with Chris Lehman from the National Atmospheric Deposition Program, have been working on putting together a project that will expand monitoring of airborne pollen. And this has particular significance right now because what we hope to do is improve our understanding of bloom times, and not only time of when things are blooming, but how long plants are staying in bloom. And this has implications in the health field. Allergists need to know when bloom times are, because for asthma and severe allergies, they like to start medication 6 weeks ahead of the pollen bloom. And it also has perhaps lesser implications for agriculturalists who depend on alternate pollen to maintain pollinator populations like bee pollen and, for example, blueberry growers. Almost all the airborne pollen monitoring that is going on today uses this rotor rod to capture pollen from the circulating air. The white box on top of this stand is the motor that drives 2 little greased rods underneath the box. And these rods spin X number of times every minute, and they capture any particulate matter floating around in the air, be that pollen or molds, spores, charcoal, whatever is available. It gives us a real-time monitoring. We know how much and what kind of pollen is in the air for a given time period, and usually that time period is 24 to 48 hours. There are some disadvantages to this, and one of them is the cost. It's a little pricey for a small lab to set up. It's someplace in the $1,700 range for this equipment, and then you have ongoing supplies. Another disadvantage is this requires some training. You need to have a basic knowledge of identification of pollen. There's a limited number of sites conducting these studies now. And because each site works independently, there's inconsistency in the reporting. Some sites, for example, here in Bangor, or in Bangor, report a predominance of tree species, while other sites will tell you what kind of tree species, be it pine or spruce or birch, is in the atmosphere at any given time. Now, the limited number of sites has real implications for Maine. This is a map that was developed back in 1990 by Janet McMahon, and it shows the 15 or 16 biophysical zones in Maine. And these biophysical zones are determined by a whole number of factors, which include temperature and precipitation, elevation, vegetation cover, and a number of other things. And this map has been reproduced in any number of places and applications. But what it is, the reason it's important to us is it shows or emphasizes the variation in bloom time from north to south and from east to west. And from north to south, from Portland to Fort Kent, bloom time for trees varies as much as 2 to 3 weeks. And from east to west, it's as much as 7 to 10 days. And I see this on a regular basis traveling from here to Western Maine. The implication of this for healthcare providers is that folks in Portland cannot judge when to start asthma medication based on the 2 sites in Maine where we do monitor pollen. The first site is up in Presque Isle. It's the Micmac Environmental Laboratory. And the second site is in Bangor in association with Eastern Maine Medical Center. We have a limited number of allergists in Maine. Most of these allergists, or all of these allergists, either work in Bangor, Lewiston, or Portland. If you are an allergist treating patients in Portland, where most of the population is located, the best information you have is pollen readings out of Bangor. Pollen out of Bangor can be a week behind pollen bloom in Portland. So it puts medical providers at a real disadvantage. And we've been working for years to try to expand pollen monitoring in Maine with no success. Now, thanks to Ivan's inspiration, we've been talking with the National Atmospheric Deposition Program people, Chris Lehman out of the University of Illinois, and NADP monitors rainwater, chemistry in rainwater in 250 sites throughout the US, southern Canada, and even down into Argentina. And the way they do this is they collect year-round rainwater. They'll collect rainwater for a week. And then there's a couple setups shown. It's basically in a bucket. And then this rainwater is sent out to the University of Illinois for analysis. And the first thing that they do is they filter the rainwater through these polyether sulfone membrane filters. They run a whole battery of chemical analysis on the rainwater and they throw the filters away. Now what the filters do is they filter out particulate matter in the atmosphere that is washed out with rainwater. And particulate matter is anywhere, anything from charcoal, dust, and pollen. So Chris Lehman has agreed to send, instead of throwing these filters away, he sent us a bunch back in November and December, and we did a small pilot study to see if this would work. And we knew it would work. We knew that we could identify the pollen, but the trick is to get it off the filters. So we came up with a couple different methods to get it off the filter, and I very fancily call the first one reverse filtration, but really what it is just washing the pollen off the filter. And it involves just turning the filter upside down in this filtering apparatus and running more potassium hydroxide and GI through it to get the cells off. Based on a very limited study, we have about 89% recovery rate using this method. Now, the second method involves dissolving the filters. If you can dissolve the filters, you get 100% recovery rate. And I have to say, I am no chemist. Anybody who knows me knows I am no chemist at all. But I've got to thank my good friends in Sawyer, Sharon and Nikki and Mike, because they will answer my inane questions. And thanks to them, we found this N-methyl-2-pyrrolidine, which is a liquid that will dissolve these filters. It's a little tricky. No, it's a lot tricky because you have to make sure you get all the water out. So not only do you use this NMP, you have to use glacial acetic acid and you need tertiary butyl alcohol. This procedure it's lengthy, it's kind of exacting, and it uses some expensive, rather nasty chemicals. The NMP will cause birth defects in pregnant women if you breathe it. However, it does give you 100% recovery. So this is more a research tool, whereas washing the pollen off is more of a monitoring tool. And you may have noticed that after you go through all this, we're splitting the sample. Part of it will store in water, and pollen will store forever in water. And part goes into silicon oil. The silicon oil is so that we can evaluate the pollen using traditional techniques under the microscope, counting the cells and identifying them. Putting them in water will allow us to use the new instrumentation that Jasmine has just brought in, the FlowCam, which uses photo imaging to identify cells. And we're hoping that we'll be able to identify and count the airborne pollen cells with this new instrument. Whoops. Now, there are advantages and disadvantages of this filter technique. The advantages is we can expand into other areas. The big disadvantage is we're depending on rainwater, so you can't quantify these results. Another advantage is that we can standardize the techniques and bring it all under one roof. And with that, I'll finish up. We have in a research proposal to the Sea Grant program to monitor sites at 19 sites across the country. If we're successful, this will totally fund one graduate student for a year to develop the program. And I'll close with this. Thank you to these folks who have supported this effort. Yes.
So Andrea, so this is so cool. And I was wondering, you were talking about the allergists in Portland. Where's the closest one to the south of Portland? I'm trying to remember. Is it like Cape Cod, Massachusetts, somewhere?
The closest site.
Pollination, yeah, current
Monitoring site, yes. I don't know the answer to that. I do know that if you go on pollen.com and look at what the airborne pollen is for Maine for Maine,
yeah,
you're getting results out of either Syracuse, New York, or Pittsburgh, Pennsylvania.
Yeah.
And there's no way of knowing that.
Yeah.
So beyond that, I don't know the answer to that.
right, because they're now participating, right?
And if the people need to know 5 or 6 weeks ahead of time, what difference does a week or two make in when it actually happens?
Well, the pollen monitoring isn't a one-shot deal. You know, it's a long-term monitoring program so that we can tell the difference or the changes in bloom time. The reason it makes a difference is if you start medication too late, it's not going to be effective. In other words, if you've only got 3 weeks of medication, it may not be as effective. Or if you start it 8 weeks early, then you're taking 2 weeks of medication that you probably don't need. And at today's prices, and that's
Well,
significant.
don't bloom times vary with you annually, or?
Somewhat, but they're pretty close, within a week usually.
Andrea, my allergy kicked in about a week ago. What's in the air now?
Poplar.
Huh?
Poplar.
Papa?
Poplar is the first to bloom, followed by acetus.
It's blooming in Orono right now.
Yep, it is.
Must be coming from.
Thank you, Andrew. Up next, we have Brian Olson, who's going to be speaking about modern diversity patterns in coastal marsh birds.
All right, so first of all, this is all results from a chapter of Mo Carell's dissertation, but she went and got a job. Yay! And I like this chapter. I think it's one of these good examples of how this sort of cross-pollination can happen in CCI, and that's just a way of me saying that if you don't like any of the geology words I'm about to say, it's Joe's fault. So. When one of the things that we ecologists really like to try and figure out are the mechanisms that control biological communities. What species are in what places? What are the areas that have lots of species? Why do they have those? Why do you have distributions of certain animals in some places and not others? And so one of the ways that we can do that real well is by trying to understand the patterns of disturbance that happen in a particular site. Because disturbance events shake up a biological community. They can take species out, allow potential for other species to move in, and they can change the membership and the diversity in those sites. But disturbance events happen on dramatically different time scales. You can talk about very short things like forest fires or storms, that are happening within a year. You can talk about decadal to millennial landscape development from humans, or you can talk about processes that happen over tens or hundreds of thousands of years from glacial cycles. So what we've been trying to figure out is what are the strong drivers for the patterns in bird communities across tidal marshes in the northeastern U.S. And the tidal marshes in the northeastern U.S. also experience a fair amount of disturbance on these different time scales. So on the short end, we have things like Hurricane Sandy. This is a picture of a marsh in New Jersey. You can see the debris field that after the hurricane passed through, and certainly those sorts of things can shake up what sorts of species are likely to be there and what their vital rates are likely to be. And then marshes across the eastern seaboard have been highly modified by humans. All of these parallel lines or ditches that were related to mosquito control were put in the 50s and 60s. And then certainly there are longer term geomorphic processes in terms of the marsh formation itself that might predict when marshes were colonized by species to begin with and where those colonists were likely to have arisen from. And so what we did is went out and counted birds in lots and lots of marshes. So here's the eastern seaboard flipped on its side from Maine all the way down to Virginia on the Delmarva Peninsula. And we selected marshes in all of these different regions and went out and had observers. Here's Mo sitting in a marsh, counting birds just by sight and by sound. Over 4 years at about 1,700 different locations. And for this talk, really what we're going to be talking about is just species richness, where we just counted up how many birds we find in a particular marsh, and community specialization. So we have a way to quantify how specialized a species is to a marsh. Is it found only in tidal marshes, or is it found in lots of other habitats as well? And then we can combine that metric across all the species found there to say, is this a specialized community or is it not a specialized community? And that will be important in a second. So we have a number of hypotheses about if we're looking at the bird communities today, what was it that made them have the particular diversity patterns that they have? And the first one would be something short, like a Hurricane Sandy. And we started our study 2 years before Hurricane Sandy, continued it for 2 years after, and the hurricane hit right in the middle of our study region. So we have a really nice comparison of communities before, communities after, and we have communities with strong storm effects versus communities with weaker storm effects. And so what we can do then is say, do short-term weather phenomena like this cause communities to change enough that you actually have to know these sorts of disturbance events on the time order of years to be able to predict what birds are at a particular site. So we have storm surge height collected by NOAA across this area, and we also have a before and an after kind of scenario. So we can say, how do things change relative to how strong the storm was there? We also looked at more of like a decadal scale disturbance in terms of the amount of marsh modification. For this particular study, we looked at, if we're surveying birds up in this marsh here, how many tidal restrictions exist from there downstream. And the reason that we focused in on this is another manuscript of Mo's, which is in revision at Conservation Biology right now, has shown if you look at particular species, their population trend over the last 15 years or so is very different from marshes that have no tidal restrictions versus marshes that have a little versus a lot. So tidal restrictions seem to cause population decline in a number of species in the marshes, so they might then cause effects not only on species, but on the communities that those species end up making up. And then this is a graph you've seen probably if you've been on enough CCI field trips. So what we have here, time on the x-axis and relative sea level on the y. And we know that the geomorphic history of tidal marshes is different across our entire region because the patterns of sea level rise are different. And if you saw Laura's talk on marsh accretion yesterday, then you'll know that marshes have the ability to actually gain level as sea level rises slowly, but they can't handle drops because then they just turn into upland habitats. And so the beginning of marsh formation was much earlier if we're talking about the southern part of our region in eastern Virginia than it is in southern New England versus around Maine. And this is through work by Joe and Dan and others in the southern region. And so what we can expect then is different patterns across this region because of the timing of marsh formation. One of the things that's related to that is marshes are particularly different sizes as we move across here. Part of that's related to timing, part of that's just related to the glacial processes in general, in terms of removing all the topsoil. And so we have much larger marshes, size on the y-axis here, just moving from south to north on the x-axis, much larger marshes down south than we do up north. So here are here's Maine, here's down in Maryland, same spatial scale here, and so this is actually Popham State Park. So there's a couple of little marshes down at the ends of estuaries, and that is a marsh. Actually, that's only a piece of a marsh. The marsh is bigger than that. So when we get down, there's lots of differences, and this means in terms of your ability to hold a population of birds and to hold specialist birds could potentially be driven by these sort of processes as well. But there's one more thing related to timing that could be important from these longer scale processes, and that's that aside from the fact that we have newer marshes up under areas that were glaciated, here's the LGM right here, we also have a scenario where because these are older marshes, these could be potentially biological refugia where species were hanging out and were able to colonize north after that. But because marshes take a while to form and terrestrial habitats are formed faster, we have birds that move north quickly and then are hanging out up here waiting for the new marshes to show up after those processes to keep getting going. And so these marshes in the northern area can be also colonized by generalists that occupy lots of habitats, whereas marshes in the south may be having these specialists because we have large patches and they were hanging out there anyway in a refugial population. So we might expect from that sort of scenario that as we go from the south to the north, if we're talking about specialist species, we should have lots of them in the south, few of them in the north. If we're talking about generalist species, we should have few of them in the south and lots of them in the north. And then we'd expect some sort of maximum diversity and at the overlap zone somewhere around the LGM. And that's exactly what we find. So here is latitude, here is rarefied richness, which is just a modified way of just looking at the species count. And we see that there's a lot of scatter going on here, but there is this quadratic trend where there are more species in the middle than you find either in the southern marshes or the northern marshes. And if you solve for the peak of this curve, it is right at the LGM. This dotted line is the LGM. It's not the peak of that curve. So you can kind of see how those two things overlap. And using some partial R squared variance partitioning, we can see that these are the amount of variance in the community data that's explained by our different hypotheses. Hurricane, there's no difference. We can't even tell the hurricane happened. Tidal marshes like hurricanes. We're all good with that. The tidal restrictions, 0.2% of the variance is related to tidal marsh restriction. Not a big deal. The latitudinal quadratic pattern is about 22% of the variance. And patch area, which we controlled for across everything, we actually only end up explaining about 1% of our variation after we have this latitude scenario going on in there. But to kind of add to that, it's not just this quadratic trend. We do see this trend in specialism as well, where this is that index of how specialized is your community, with high specialized communities and more generalized communities. And these, you can see that there is this slight trend where as you go south, communities become more and more and more specialist, even though diversity is peaking in the middle here. So we see that contemporary disturbance to tidal marshes explain very little in the way of variation in bird communities. We see that geomorphic features at subcontinental scales explain a lot more than these contemporary patterns. And we see that specialism in birds peaks in the south, while generalism peaks in the north, and those together make diversity greatest at the LGM. And this is consistent with this sort of two-stage colonization hypothesis. So I just want to thank our funding sources. All this tidal marsh stuff is a huge team of PIs across many institutions, otherwise we wouldn't be able to pull this off. And I really want to shout out to Betty, Lee, and Becky, because this is one half of our field crew from one summer. So the amount of HR paperwork that I run through that office is frightening, and they're very helpful. So with that, thank you.
Brian, you said that commented on marshes don't survive a sea level fall, and then said this is why marshes are more prevalent in down south. But there was sea level fall there too.
Yeah, we're talking about this a lot. So there's some conflicting evidence in terms of what folks think happened from the marshes standpoint, and what the genetic patterns within the birds suggest have happened evolutionarily over the same time period. And so, Joe, you can feel free to jump in at any time. You want to just get your gun?
Yeah. There are undoubtedly fringing marshes as sea level fell. Right. Marshes were restricted to the tidal range because they are restricted to tidal ranges. Whereas when sea level rises, they build peak deposits up and can expand the spatial extent of their range. They're still restricted to the tidal range because they can accrete peak deposits during the rise, not during the fall. They can have a much larger area.
So the question ends up being, if there was enough marsh around during this period to actually hold on to bird populations, or whether bird populations would have to have existed in other habitats at the exact same time or not. And it's really difficult to say. But it is interesting that one of the specialist species is actually it's the one that seems to have existed the longest in this habitat, or has some genetic signature of existing the longest in this habitat, is the only species that exists in the habitat zone that gets daily inundations, not the ones that only get inundations on the new moon, full moon kind of cycles. And so those are the scenarios that are those are the habitat types that are likely to have been more stable. So I think that there's some signal that there's some populations that are able to go in there. George.
I have 2 points. One, it's a matter of wording, but rather than saying the diversity peaked at the LGM, which I don't think is quite what you meant, you might say it is highest at today at the limit of Laurentide glaze ice or something.
Right. Yes, it's not.
That's probably what you meant.
Yeah.
You probably didn't mean at the LGM. But that brings me back to a point I think Roger was driving at in thinking about the southern marshes, which may well have a continuity to some older marshes, but at the same time, at the LGM, the continental shelves were totally exposed.
Yeah.
Or close to totally exposed.
Right.
So those marshes were nowhere near where they are today.
No.
And the exact concurrence or connection between those ones and today's, would be a nice project for a thesis.
I think it'd be great. Because my thought is that so certainly they existed at much lower levels, but those marshes, at least from a fringing standpoint, are tracking inland with sea level rise, and the birds could ride it. Whereas in the north, there's nothing there from a marsh standpoint. And so they have to have come from some other habitat source in order to get in. So yeah, so I show the map and say, yeah, there's refugia down there, but there's not. It's obviously it's out further. But my thought is that they might have ridden that there, but there's a lot of this could maybe have happened.
Yeah. It's a pretty good point that the birds probably came from south of the ice sheet.
Yeah.
Sea level fall also was very much more gradual in the south, so the marshes could have tracked out. Whereas here, because of the isostatic uplift, it was very abrupt.
One more question?
Along the Appalachian chain, there's several saline solutions that are creating salt-like marshes. Could that have been a refugia for these birds?
Sure.
Excellent. Thanks, Brent. Next, we have Ben Edwards, who's going to talk about using a diverse proxy in Peru.
So thank you for allowing a few interlopers from the south to come up and be a part of this. This is the first time I've been to the University of Maine, but we have some growing connections between your university and where I teach at Dickinson College in southern Pennsylvania. In particular, Kristen Strock is now a professor in the Environmental Sciences Department. And we've had students going back and forth a little bit, and I'm actually up here with a graduate and a soon-to-be graduate that are looking at grad school here. So in the future, we certainly might have even stronger connections. And in part, my work in this has been driven by another connection between our two schools, and that is the Churchills. A lot of you know Dan Churchill, who helps fund a lot of research here with graduate students. He was a graduate of the University of Maine. His wife, Betty, was a graduate of Dickinson College, and so they've also been very generous for supporting our college. And we're very interested in continuing to find ways that we can hopefully collaborate with people at UMaine. We have a number of people that do climate change research at Dickinson. And what I want to do today is give you a brief overview of a project that involves many different time scales, many different types of research, only one of which I'm an expert at. So Will can answer some questions. If you have questions about his study, he had a poster yesterday. He's been looking at modern changes to the ice cap. This is Nevada Corapuna, which is in south central Peru. Kristen, who can't be with us because she's got a new family member, I'm sure she'll be here in future years, but she is involved with a couple of the students looking at diatoms and some core that Will and I collected last year from a small lake by the western side of Corapuna. And then a lot of my work, and this is how we got involved with the Observatorio Volcanologico de Ingamet, which is a relatively new volcano observatory for Peru. They're interested in Corapuna because it's the largest ice cap volcano in Peru, and there are lots of hazards associated with future eruptions of the volcano. And that's how I got involved, because I'm a volcanologist, igneous petrologist. So what I want to do, I'll give you a brief summary of glaciarized volcanoes and why I think they're important, and they may be of interest to some people that study climate change. They're particularly important from the hazard perspective because there are over 180 glaciarized volcanoes that we know of that are potentially active, and a lot of these are in South America, and they're in places where eruptions through ice can produce lahars, produce floods. There was an extreme example of this, 1985 at Nevada del Ruiz in Colombia, and some of the lahars came inundated towns and killed over 23,000 people. So these volcanoes are particularly hazardous. But they also, and what I'm going to focus more on, they're kind of unique because they preserve records of climate at a number of different time scales. And so I'll tell you a little bit about that in general in just a second. And then most of my talk will focus on results that are somewhat preliminary, but also some coming to a close on the work we've been doing at Corapuna. So I've been working with, I've been very fortunate to have an incredible student, Will Kochditsky, who's been working with me the last couple of years, and Will's got great computer skills in a number of different areas. One of them is building databases in ArcGIS. And so we were interested in trying to figure out how many glaciarized volcanoes actually occur on Earth. And so we did a very simple approach by looking at one of the relatively new global glacier databases. And that's shown right here. The glaciers, for this database, there's basically a center point. So we're not actually looking at ice outlines. And we combine that with the database of Holocene volcanoes, or volcanoes that erupted in the last 10,000 years, which are considered to be things that could be active, and basically searched where these two things coincide to be able to produce, we think, probably the first global map of glaciarized volcanoes. And so the volcanoes, we've searched for volcanoes that basically had ice within 1 kilometer of the main vent of the volcano, volcanoes that have ice within 2.5 kilometers, and volcanoes that have ice within 5 kilometers. And part of this is from a hazards perspective. If ice is close up to the volcano, when it starts to become active, there's a different set of hazards you have to consider. But it's also important for the impact on ice and impact on people that depend on ice melting during the summer to produce water for agriculture and things like that. We know there's lots of economic costs from eruptions from ice-clad volcanoes. The Eyjafjallajökull eruption in 2010 in Iceland, even though it was a really small eruption, caused hundreds of millions of dollars in economic cost to Europe and stranded lots of travelers. And there's a spectacular eruption from Villarrica volcano in Chile last year. There are some moderate-sized towns by Villarrica, so big eruptions can produce lahars that can cause mortality. But in the last 50 or so years, glaciarized volcanoes in general have had relatively high mortality rates because of their flooding. What I've worked on for most of my career is somewhat longer-term climate change studies from these volcanoes. And as you are all pretty well aware, one of the interesting things about trying to understand Earth's climate is trying to go back in time. So for the last glacial maximum, we can look at moraines. A lot of people here have been doing that and looking at precession of last glacial maximum. And moraines are a clear record of where ice was 15, 20,000 years ago. However, we have indications from the oceans, and this is the Lysecki-Ramo set of curves looking at changes in essentially ocean water volume through time. And we don't have much of a terrestrial record if we go back past the last glacial maximum. Moraines just do not survive very well, the coming and going of the glaciers. So what I work on and what I've done for quite a while is looking at volcanoes that have erupted underneath these now extinct ice sheets, looking for specific kinds of deposits that allow us to identify that there was ice when the volcanoes erupted. Sometimes we can get constraints on how thick the ice was, and we can actually go back through time and try to get an idea of, for many of these older glaciations, try to get an idea of actually where ice was, which we don't get from these sea level curves. All we know is something about the volume of ice from water that was gone from the ocean, but we don't necessarily know where the ice was. And this is a diagram I have in preparation right now. I'm trying to compile records from across mostly North America, but also a bit of South America, trying to look at glacial deposits that have been dated, where we know that there was ice contact during an eruption. And these are, the black dots here are all part of sort of a recent dating effort. And there are many interesting things that we can get from these records in areas where there are lots of volcanoes. If we find two that have essentially the same age, we get an idea of the spatial distribution of the ice. 700,000 years ago, for example, in northern British Columbia, which is where I do a lot of my work, where the Cordilleran ice sheet was sitting, we have 2 or 3 different volcanoes that all had subglacial eruptions at that time. So we can start to get an idea of spatial distribution, ice thickness, and we can even track back the existence of ice, in particular for the Cordilleran ice sheet, to 2.8 million years, which is one of the oldest dates of ice that we know of. And I say it that way because when these volcanoes erupt with their textures, we know that we're actually dating the existence of ice, because the textures only form when the volcanoes erupt under ice. So that's sort of long-term why these types of volcanoes are important. Focusing in on Nevada Corapuna, it's just north and a bit west of Arequipa. And this is a map that Will has made, showing lots of important aspects. These are population centers, current drainages that could be affected by future eruptions. There are also drainages where people rely on Corapuna for water during the summer. And Nevada Corapuna is very important for a couple of reasons. It's been named as kind of one of the sentinel ice caps for tropical glaciers. And so people have looked at it very carefully to try to get an idea of how fast it's retreating. It happens to be in a part of Peru that's relatively dry. And that's important because it means every time Landsat goes over it, you get pretty good pictures. And Will can tell you lots of details about the studies he's done, but he's been able to process over 200 images in the last 30 or 40 years from Landsat to look at the record of how fast the area of ice is shrinking, and also getting some information about yearly snow cover, which is important for things like effects of ENSO. So this is Will's undergraduate thesis. He had a poster yesterday. Hopefully most of you saw it. He had sort of 2 really important finds. One is that the ice area at Corapuna seems to be shrinking quite a bit slower than previous estimates. And this is important because Corapuna has been cited by the IPCC reports as being a tropical ice cap that's at risk because they think it's going to go away very fast. And Will's showing, I think, relatively clearly that the ice is not actually retreating as fast as people had thought in the past. And this is important because people are making policy decisions based on how soon people need to adapt in this region, because Corapuna is a really important ice source for water to sustain agriculture. So those are great results from Will's work. And this represents the kind of thing at these ice or glaciarized volcanoes that you can do looking at climate change on the decadal scale. What's happening with satellite records to see how fast the ice is shrinking. And so that's sort of the most recent time scale where we can get records. We can also get longer time scale records by looking at places like Lago Payacoca, which is a lake at the western end that last summer, as part of our expedition to the volcano, Kristen taught us how to core lakes. So we borrowed her equipment and her raft, hauled it down to Peru up to 15,000 feet, and we successfully got 2 cores from what we think is one of the deeper parts of this lake. Lots of interesting things about the cores. I'm not a diatom expert, but I'm learning a bit. But one of the interests, and of course, Kristen's in charge of looking at the diatoms, and she's had studies doing population estimates. One of the really interesting things about the core, to me in particular, is this lake was covered by probably 2 centimeters of ash in 1600 AD on the 19th and 20th of February. Maybe a day or two after that, but that's the date of the Plinian phase of the eruption at Huanaputina. And so we have this incredible time marker in the middle of this core that we know very accurately when that ash started to fall. And so this allows us to date the core. We think based on this, the core has a record of over 1,500 years. This is just one of the counts from Sydney Diamond, who's working with Kristen, and they're going to present this in more detailed research later this month. But they're looking at how diatom species change through the core, and there's a couple different indications of climate effects. We're also looking in particular what happened to the lake when the volcanic ash hit. And I'm not an expert in reading diatom charts, but one of the interesting things for sure we see is there's a big change in organic carbon. So the ash may have killed off a lot of things in the lake, at least temporarily. Finally, this is the thing I'm more interested in, and this is trying to tie together work from lots of things, including work Gordon's done at Korapuna. But essentially, we can take a combination of records from things like moraines and dating, dating exposure ages, combined with dating lava flows, and actually finding lava flows. These flared columnar joints are pretty indicative of ice contact. We've got lavas coming out of a lot of the tops of the volcanoes that look like they were ice-confined channels. And so this is going to allow us, hopefully, in the future to take the climate record of Korapuna back into the Pleistocene. We don't know how far back it'll go. We found evidence of this is a place where a lava flow came over a block of ice. And so this is an ice mold and lava flow. And this actually looks like it may have been used by paleo herders. We found some pottery shards and things like that. So there's interaction between volcanoes, ice, and archaeology here, which is pretty fascinating. So ultimately, these volcanoes are important because when they erupt, if they have these features from ice contact, they're dating the existence of actual ice and sometimes even give us constraints on ice thickness. So they represent really important climate storage areas for climate proxies. And Korapuna is one example that we probably can look for in other places as well. We can get a picture of climate over many different time scales. And that's it.
How do you factor in the idea that these are hot spots under glaciers in terms of the hot spot effect on the accumulation and so forth and demise of the ice versus weather conditions or atmospheric conditions?
So that's a very important question. One of the reasons why I'm glad to be up here, because I need to meet more glaciologists so they can teach me more about how ice behaves. But I think that's pretty important because looking at ice changes in ice obviously are important when Will is doing his studies to get some sense of is this actually a climate effect or is it not? The youngest eruption of Korapuna we know of was about 1,000 years ago, give or take. There's not much seismic activity. So there's not much to indicate that there's an excessively high heat flow there right now that would be affecting what we're seeing with the ice cap in the last 50 or 100 years. But as a monitoring tool, it might actually be very important because an ice cap might respond, maybe in a subtle way, but might respond more quickly than some other indications if a volcano was starting to become active again. So it's a good question.
Two aspects of this question. Why do the flared columns indicate ice contact, and what other evidence of ice contact do you see in the volcanic deposits?
There's actually a whole class of volcanoes that are called tuya volcanoes, but the whole morphology of the volcano basically is due to eruption in a lake, typically in a spot where there's no evidence that there could be any sort of a lake without ice. Sometimes it's a bit of interpretation to say, is it a proglacial lake versus an englacial lake? But in those places, you actually find pillow lavas. So there are places in British Columbia where there are ridges that are at 7,000 or 8,000 feet and the whole ridge is pillow lava. And you have to have water to generate pillow lavas, so you have to find a way to trap water. the flared columns and partly also the size of the columns we think reflects non-uniform cooling rates. And in general, with lava flows, those columnar joints we think are smaller when you have a faster cooling regime. And so having water around enhances the rates of cooling. And so we think that's how you get those distinctive columns. Thank you.
Thanks, Ben. So we've got coming up, we're a little bit behind schedule, but that's all right. Just want to make sure we leave plenty of time for Richard's lecture and also for lunch. But coming up, we have some quick talks, so we'll try to move through these relatively rapidly, not too rapidly. But the first one is going to be from Sudarshan Chawate. Right.
All right. Just good morning, everyone. So this is a short talk. It's preliminary work, so I don't have any real results or things of that sort. It's more of a look ahead at where I hope to take some of the development on the P301 project that Mark has talked briefly about, and also Mark is the one who does most of the work as well. So again, the main motivation is increasing amount of data, and the issue is that at some point the increase is large enough that we need to do things differently qualitatively. Up to a certain point, we can just make things faster and do things a little bit faster, and that works. But when we have orders of magnitude increases in data set size, we probably need to think about qualitatively different approaches. And so, so just one idea that I hope to describe very briefly is taking what in computer science circles is called a language-based approach, which is certainly not the only approach, and quite frankly, I'm not sure is the best approach, but I think it is possible that it is a very good approach, and so that's something that I hope to investigate. So what do I mean by a language-based approach? The basic idea is to have a formal language for describing the kind of patterns that we might find interesting. And this is not to suggest that this would be an automated system for discovering interesting patterns. This one way to think about it is that this would be a sort of first cut. That would be, well, you know, ideally we want to look at everything, but if you just do some simple arithmetic, you figure that unless you plan to live for 1,000 years, that's not going to work. So you say, well, you know, I need to prioritize the things I want to look at. And so this would be a way to do that prioritization. And whenever we talk about formal languages in a computer science context, we basically think of three aspects. One is what are the primitives of the language? The second is how can you put those primitives together to compose more interesting concepts from the primitive concepts? And the third, which is actually the most interesting, is how can you abstract so that the operations that you're performing, instead of performing them on these primitives and composed primitives, you're actually performing them on substantially higher level concepts. In terms of motivation, I'll skip over this. So the basic idea is to break up a stream of data into some kind of tokens. This is an optimization, so there's going to be some loss of information here, and then to describe the patterns in terms of patterns of these tokens. There's many ways to do this. The initial investigation, I'm focusing on regular expressions, which are very well studied in computer science, and that's part of the reason. The other important thing about regular expressions is that they are a kind of a sweet spot in terms of being complex enough to allow us to express a lot of interesting things, but not so complex that we cannot reason about them automatically. And so there's always we need to strike a balance between these two aspects. I'm going to skip over the examples and things like that, and I'll skip over the implementation as well, except to note that I think I'm Mark's first real user, if I can be called a real user, and I already bugged him about some things about his API. So in summary, what I'm proposing is basically a linguistic, from a computer science point of view, a language-based approach to thinking about patterns as a way to filter them, as a way to prioritize them for essentially any kind of sequence data set, but my primary focus is on ice core data. And I will also mention that this preliminary work was featured a little bit in an honors thesis by one of my undergraduate students, Nathan Dunn. And for Andre, in fact, was on his committee, and so I'll also thank my collaborators and my funding agents. Thank you.
All right, next we have Ellen Enderlin, who's going to be talking about ice melanges in glacial fjords.
So I realize that I have jargon in my title. So to clarify everything, I'm a glaciologist. I'm really interested in this guy down here. This is a glacier that is flowing out into the ocean. But in order to understand what glaciers are doing, we have to figure out what is going on in the fjords as well that they're draining into. And so this up here, this is actually a fjord. The water is covered by icebergs. And so that's why it looks like this little white mess up here. These glaciers are pumping out so much ice into these fjords that the ice just can't be evacuated away fast enough. And so I want to look at these icebergs and figure out, well, are they melting so much out in this fjord that they're actually influencing the heat that gets delivered to these glaciers? And that may in turn control how quickly the glaciers are flowing. So there could be this possible feedback that's going on. And so that's what I'm really investigating here. And I'm looking at ice melange. So this melange is this matrix that you see of all of these icebergs and like little bits of icebergs and sea ice that are packed together in these fjords. And I believe Gordon will be showing you some more pictures and laser scans of this area later on. So I'm interested in looking at these icebergs and how they're melting. And so to give you some sort of perspective on this, this was taken when I was flying in a helicopter over the glacier. The fjord is probably about 5 kilometers or so wide, and this melange stretches for about 20 kilometers. So this is really, really an extensive area covered by these icebergs. And so I'm interested in looking at the fresh water that's coming off of these icebergs, if that's influencing fjord circulation and therefore heat to the glacier. So in order to get this freshwater flux, this volume of water that's delivered to these fjords from melting icebergs, I need to know the submerged surface area of the bergs and their melt rate. And if you just think about it here, I have this example with all these glasses with ice cubes sitting in them. This one will melt a lot faster because the ice cubes are broken up into bits, and there's a huge surface area here, versus this one down here where your surface area is really quite small. So I need to know my submerged surface area. And I'm getting that from really, really high resolution digital elevation models. I have an example here. This is a digital elevation model just over the part of the melange that the DEM covers. And the blue colors are the sort of background elevations. And then you can see that these redder colors, these are big icebergs that are sticking up. And these DEMs are about a 0.5 meter resolution, so I could lay on the ground and you could actually have a DEM of me. So these are really high resolution, and I'm sure they're actually really helpful for a lot of the studies here. So if anyone wants to start using these, please feel free to contact me, and I'm happy to work with you on implementing them into your work. And I'm using them to figure out the submerged area, which I have to figure out iceberg size and all kinds of complicated things, but stick with, I need the DEM here. So also using these DEMs, I can look at changes in the iceberg elevation over time. And they change elevation as they're melting, they're starting to ride lower and lower in the water. So I look at that change in their elevation over time and I figure out the volume of ice that they're pumping out into the ocean. That's what's plotted on the Y. And I estimate their submerged area as well. That's what's on the X. So these plots are for 2 different fjords. If you look at these slopes of their lines, that's basically telling you their melt rate. You can just see that they're melting at very different rates at different time periods. But you get an idea, they're melting pretty quickly. It goes up to about 0.8 meters per day on all of their sides. So when I combine these things, I can calculate the submerged area of the melange. I figured out it's way larger than the glacier terminus, so there's probably a heck of a lot of melting going on. When I look at the melt rates, I said they go up to 0.8 meters per day. And when I combine those two things, I get freshwater fluxes that are on the order of 100 to about 2,000 cubic meters of fresh water going into these fjords each second. An Olympic-sized swimming pool is about 2,400 cubic meters. So you're putting almost an Olympic-sized swimming pool of water into this fjord each second. This is huge, and it tells you that the melange melting may contribute more fresh water to these fjords then surface melting over the entire glacier surface. So this could be something that's really important and no one has ever really looked at it before. So I will end on that and say this is preliminary work, and I'm happy to work with other people to work with these DEMs in your studies.
Any questions for Ellen?
So, Ellen, did I catch you right that what you're looking at is the change through time of the height rather than trying to count each iceberg?
So I'm looking at the melt rates are actually from individual icebergs, and I am picking them out, changes in the height of the individual icebergs, because you can't really just scale it up to the whole melange because there are new icebergs coming in all the time, there are icebergs breaking out. So it'll change in sort of like average elevation, totally independent of melting as well.
So how do you deal with the small ones that you're not actually measuring then?
I do make sure to measure some small ones, and I found that they do melt at a slightly lower rate because the water masses up at the top of the fjord tend to be colder temperatures than the ones at depth. So you have to sort of get a good variety in there.
Once they're in the water, they're not changing sea level just because they melt, obviously. So how does that fit into the sea level story? I'm not so sure what you meant by that.
So it fits in with sea level because once they're floating, yeah, they're not changing sea level at all. But as the glaciers are pumping out more and more of them, the glaciers are actually shrinking. So their mass loss is contributing to sea level. And so I want to see, okay, are these
the rate of mass loss?
So it's not really the rate of mass loss, but it's whether or not you're pumping out more ice into the ocean, sort of like mini Heinrich events almost. You're pumping out more ice into the ocean. Are you actually affecting how much heat then gets delivered to the glacier to cause it to pump out more ice into the ocean? So seeing if there's a positive or negative feedback going on there.
I presume that there's a layer of fresh water coming out of the fjord into the Davis Strait. Anybody looking at that layer, the distribution of that fresh water? Thickness
So people do
mixing?
try to look at the water masses going in and out of the fjords. It's really complicated because the fact that your moorings just get battered by icebergs and crushes the heck of a lot of people's moorings. So there are some observations, but then they don't tend to actually get observations way up to the surface layer. So normally about the top 50 meters of the water column is unsampled, which means that we have really no idea how much fresh water is coming out as a sort of surface layer from the icebergs melting.
We could get some of that
We have
by
to stop
tracking
here,
icebergs.
Ron. We're way behind.
Next speaker is Andre Korbutov, talking about crypto tephra in Maine.
Good afternoon. So there's another crypto title here. Crypto, small tephra, it's something, any ash that come out of volcano will be called tephra. And it's a little short update on the project. So a couple of years ago, we learned that people from Europe found tephra, so volcanic ash that was transported for thousands of kilometers and was deposited in Maine peat bog. So they found it in one site, and potentially application for these tephra layers could be, we could track these little time markers and actually estimate how fast this peat was deposited. It could be done here in Maine, and if we develop new method, it actually could be applied in a lot of areas, because it's one of the actually big unknowns now, how much carbon gets accumulated over different time intervals and how fast it happens and what's actually controlled it. So several of us like trying to figure out how to get funding to do that. And again, this is a couple of slides that summarizing this activity. So you see these volcanic centers, and some of them actually as far as like West Coast, Alaska, and there's a little place here, and people found all these very small particles. They're about 20, 50 micron in size, and they geochemically fingerprint the source. So just this year, another paper came, and as they have more layers. Now they added Kamchatka volcano, like 6,000 years ago event, and also something from Japan. So the idea here, if you get funded, we should be able to work and establish like a local geochemical tephrochronological database, and people could use it. We try a couple of things. We try this international collaboration program, and they're really happy to take us, but none of the programs in NSF actually want to support us. Like Paleoclimate basically have no interest in TEFRA. That's what they like. So we were lucky enough, we submitted one proposal to this educational program at NSF recently, and the idea was we're going to have students who are going to go and help us to look for these layers, and we're going to help them to establish and get them trained in methods. So idea they're going to collect cores, they're going to process core, work with data, and that's like a short time interval during the summer we're going to have them over. So we obviously submitted it. We probably will not be funded, but MRI, that's another approach we did. Again, the idea here, we're going to acquire this laser ablation system to work on TEFRA, potentially to benefit other groups. But one of the angles here was that we actually have expertise working on Antarctica and some other regions with the TEFRA, and we actually have, I think, way better expertise to dealing with order of magnitude smaller particles in Antarctic ice cores. So obviously, our expertise will be valuable here. And again, the idea here, the take-home message, if you work with speed bumps here or work with some other medias and you think you might have a TEFRA layers, we'll be happy to look and maybe work together. That would be it. Thank you.
All right, next we have Ivan Fernandez.
He was supposed to read my title to use an extra minute of mine. So I'm going to give you a short update on an activity, we'll call it. It's not a singular study. Hopefully everyone in the room is familiar with what that plot represents. It's SO2 emissions and NOx emissions in the United States, which have gone down. The younger ones in the back of the room probably don't remember when Congress passed legislation which could do positive things like improve the environment. There's an example of it. In Maine, we probably have about 60 to 70% decline in sulfur deposition and 30 to 40% decline in nitrogen deposition. And there's a large body of work looking at the response. We call it recovery, but it's uncertain what we're recovering from since so many of the other curves are going up. But nevertheless, we're living through a remarkable time relative to ecological response to certainly atmospheric vectors of change. Deposition's gone down. We've seen evidence of recovery, not full recovery, but partial recovery. We've heard a little bit about it here. Jasmine Saras is one of the famous scientists that's contributing to understanding surface water response, but to present, we really haven't had evidence of the initial recovery or the signs of recovery in the terrestrial environment. And so there's a network of 27, I think roughly 27 sites. These are all forested, mostly watersheds. The circled one there is one of the ones that we run in Maine. It's the paired watershed study site at Bear Brook, which I'll come back to in a second. These are all part of the Northeast Soil Monitoring Cooperative. We've been around for about 10 years. We meet every March in Troy at the USGS headquarters. This year was the 10th year. We had a celebration. We had a cake that looked like a soil profile. It's not dirt. It's not a sediment. I think Dan left, but it's not a sediment. It's soil. In order to celebrate the fact that it's uncommon that you have soil measurements over time. We monitor a lot of things that are easy to measure. Measuring soils, and particularly in landscapes, is not a matter of going out and just taking one hole in the ground. So you spend, months and months and months getting collections of these samples. And what we reported and published on this past year is the first evidence, to our knowledge, of initial recovery in the terrestrial environment. And so all of us have measured data on soil change over time and on deposition. And what that plot is showing you is the proportional reduction. Those are ratios, and I won't take the time to get into it now, but it's basically showing you that the decline in labile aluminum in soils, or the active or exchangeable aluminum in soils, the decline is proportional to the amount of sulfate deposition decline that we've seen over that same time period. There's also increases in pH and base cations, not as continuously as that. So aluminum's a big deal in soils. We've got a lot of it. Organisms don't like it, both in the aquatic environment and in the terrestrial environment. That's empirical evidence of this. And in this bar chart, the very first set of bars there is the average of all of those. And so the black bar shows you what it used to be like relative to the labile concentrations of aluminum in soils. The gray bar, which is shorter, you'll notice, means that the concentrations are lower. And so aluminum's going down, labile aluminum, not total aluminum. At our Bear Brook watershed in Maine, the reason I circled it before, these two sets are from softwood and hardwood stands or components of our forested watershed. That's the reference watershed. It's part of that body of data, and it's showing you exactly the same trend, that aluminum is going down. The last set of bars show no significant difference, and those are in our experimentally treated watershed. We affectionately call it West Bear, and every 2 months we fly a helicopter and treat it with nitrogen and sulfur, and we've been doing that for 25 years. And so that's sort of what the environment might have looked like had we not had the recovery. It's probably a little higher than what the environment would have looked like. And so that's experimental support for what the empirical data has shown as an initial emerging recovery across that landscape. And so this cooperative is, we have a proposal out now, and we will continue to evaluate this response. And we're particularly interested in the intersection, of course, between declining sulfur and nitrogen deposition and rising CO2, which is a fertilizer for plants, and all the things we know about relative to the changes in precipitation and temperature. I'm done.
All right, next we have Jasmine Saros, who will be speaking about quantifying the role of lakes in the Arctic carbon cycle.
Thank you. This is just a short update on a new dimension that we're adding to our lake research in the Arctic, and that is to try to contribute to quantifying the role of lakes in the Arctic carbon cycle. And so even as recently as about a decade ago, this was the thinking about the role of inland waters in the global carbon cycle. In other words, that they essentially did nothing in the global carbon cycle. So they were just a passive pipe through which carbon passed from land into the ocean. And then a series of synthesis papers came out between 2005 and 2010 that really changed the way that we think about the role of lakes in the global carbon cycle and demonstrated that they're actually quite important in the global cycle. In particular, lakes can bury carbon in their sediments, but they also release carbon dioxide and methane to the atmosphere. So they are very reactive sites for carbon processing. This modified paradigm was derived from data that came from hundreds of lakes, most of those lakes situated in northern mid-latitudes. There was one Arctic lake, Tulip Lake, that contributed to deriving these numbers. And there's good reason to think that we need to better integrate Arctic lakes into these models. First of all, about 25% of the global lake area falls in Arctic and subarctic areas. So they're an important region in terms of being very lake rich. But as I said, we need to think more carefully about how carbon cycles in these systems, because there is some good evidence that the cycling here is quite different from what we see at mid-latitudes. First of all, these in the Arctic, these lakes receive old carbon from thawing permafrost. That old carbon has different reactivity than what we might see for fresher carbon. We also know that the efficiency with which carbon is buried in Arctic lakes is actually very low, and it's unclear why that burial efficiency is so low. We also know that dissolved organic carbon concentrations are actually decreasing in a lot of Arctic surface waters, and we've demonstrated this in lakes in southwest Greenland. This is opposite to what we're seeing in mid-latitudes, where DOC concentrations have actually been going up over the same time frame. So it raises the question of where that organic carbon is going. Is less of it coming into lake ecosystems? Is more of it being buried in those systems? Or is more of it being lost as carbon dioxide and methane from those systems? So this summer, we're going to be starting to try to put some better numbers at least for these Southwest Greenland lakes on the carbon sampling there.
Okay.
All right, next we have Carl Kreutz talking about a 40,000-year ice core.
Yeah, just a brief update on a relatively new project for us. As the title of this suggests, it's a new ice core being recovered from the South Pole, and it's really a very large collaborative effort, one of the community-based efforts from the ice core group around the U.S. to recover this core. Our group is from the University of Maine, from Dartmouth, and from South Dakota. And this picture here, I should note, is in fact a piece of the new South Pole ice core. The picture was taken by Dom Winsky, who probably many of you will remember did his master's degree here at CCI a couple of years ago, and he's now doing his PhD at Dartmouth and was one of the drillers at the South Pole this year. So he was instrumental in recovering the core. Our motivation for being involved in this project really stems from this figure. This is some work that Bess Kaufman and I put together a couple of years ago. Essentially what it is are 3 different deep ice core records of dust concentrations in the atmosphere going from today on the left-hand side back about 60,000 years on the right. So these are 3 different deep ice core records, 1 from West Antarctica and 2 from the plateau of East Antarctica. And there's lots of different reasons to think that these 3 curves should not look very similar. But in fact, when we put this together, at least on millennial timescales, we were quite surprised to find that there's a really good correspondence between these 3 curves. So it's telling us something about the way that climate and the atmosphere and the transport of dust through the atmosphere occurs in the southern hemisphere. We don't have all the answers yet, but we're hoping that some data from the new South Pole ice core will give us some extra information on this. And I should note, somebody earlier today mentioned the International Partnership for Ice Core Sciences. The past 40,000 years is still a key time period for that group, so it's really a target for the international ice core community to develop more records to further refine our understanding of this time period. So before the ice core was ever the drilling ever started at the South Pole, we already had a lot of good information on the age of ice at a given depth in the South Pole, or around the South Pole, and that's because astrophysicists have drilled something like over 50 deep holes in and around the South Pole to install their own instruments, and I think the ice core community is quite happy to take advice from astrophysicists. So we already had a good idea of how deep we had to drill to get back 40,000 years, and it turned out to be at about 1,500 meters. So 2 years ago, the crew got down about 700 meters with the drilling, and this past season with Dom, they got down to 1,500 meters, and the drill crew was happy, and NSF was happy, so they kept going, and they ended up at a depth of 1,751 meters, which should push the age of the ice back to about 50,000 years, so a little bit of extra bonus ice at the bottom. So the samples from all this are just starting to be processed now and coming into our different laboratories, so hopefully we'll have some results soon. That's where we're at with it. Thanks.
All right, we have one final update from Gordon Hamilton.
Okay, this work is going to follow on a little bit from what Alan talked about a few presentations before. So we're, as you know, working in Greenland's glacial fjords, trying to understand the processes that are driving the rapid changes that have been observed at the margins of the ice sheet over the last decade. This rapid increase in speed, rapid retreat of the glaciers back up the fjord, and this pumping of icebergs out into the ocean, and some means to drive rapid rise of the sea level. So we're trying to get a process-based understanding of how the mechanisms work. The way to do that is actually to collect very detailed data. Ellen provided one mechanism to do it, is to fly satellites 700 kilometers above the Earth and make very detailed observations on the Earth's surface. But then you're constrained by the orbit characteristics of the satellites, and you may at best only get one or two observations of a glacier like Helheim Glacier per week. We know from measurements that we've made on the glacier itself over the last 10 or 12 years is that the glacier is able to change its speed on timescales shorter than 1 hour. So in order to understand the processes, you need to make measurements on very short timescales. So our approach has been to develop a tool here that's sitting on a safe location overlooking the glacier, and it operates by sending out pulses of light, photons of light, and sending them out, looking at the returns coming back from the glacier, using that to construct a very detailed three-dimensional map of the glacier surface. It's a process called laser scanning or terrestrial laser scanning. And by doing this, we're able to repeatedly map very large swaths of the glacier terminus pretty much as quickly as we want. But in this particular application, we're doing it once every 6 hours. So the system's called Atlas, Autonomous Terrestrial Laser Scanner. So laser scanning is not a particularly novel technique. You can go online and you can buy a terrestrial laser scanner if you so desire. But we had to overcome two fundamental physical limitations. First is that most commercial laser scanners use red lasers. And red lasers, you'll know this from your optics classes, gives very poor returns over snow and ice. So if you send out a photon of red wavelength light, chances are it's not going to return back to the detector. So here's the red laser. So our solution was, because we know from optics, that if you send out photons of green wavelength light, like this, you get much stronger returns from snow and ice. The trouble is that commercial vendors don't make green laser scanners because it's not icy. Sorry. So that's one design limitation we overcame. We convinced the manufacturer to build us a scanner that operates at green wavelengths. That's the scanner there. The second physical problem we had to overcome is that the speed of light is a little bit too slow for our application. The problem is that this scanner is so sophisticated, it can throw out 250,000 photons per second. And if you're sending out green photons, they're able to travel 10 or 12 kilometers. So do the math in your head with the speed of light. By the time it's sent out one photon, if it's traveling out 12 kilometers, hitting off something and returning back, the scanner has already fired a new set of photons. And these might return off the closest part of the glacier to the scanner and get back before the first set of photons arrive back. So the way we overcame that was by tagging each individual photon with a little piece of information that tells us which pulse sent out which photon, so we can then reconstruct where they come from. So this is the setup we have at Helheim Glacier. This is a picture that was taken at 8 o'clock this morning. So the system is here. This is the scanner. This is all the power and hardware that maintains the system. Okay, so this is Helheim Glacier. This is the melange that Ellen talked about. This large pizza wedge is the swath that we're imaging every 6 hours. This is a typical digital elevation model that we can reconstruct from that laser scanning data. The system, we spent the last 2 years designing and engineering the system, and then last July we deployed the system overlooking Helheim Glacier. We take a photograph of it every hour so we can see that it still exists. The thing cost $500,000, so we don't want it to be stolen. So we keep track of it, make sure nobody's flying up there and taking it away. We can send back photographs every hour. They're cheap to do by satellite telemetry, but the scanner, every time it scans, collects about a gigabyte of data. You can't move that by satellite telemetry, so it's all stored on site. So we don't have any data right now. But one of the things that we want to look at when we get the data back in a few weeks is to look at what happens in the glacier immediately before one of these very large icebergs comes off. And here's just an example. So on the 12th of October, terminus is here. By the 14th of October, it's back here, and that's a retreat on the order of about 1.5 kilometers. So by having our very high resolution scanning data, we can see what changes took place in the glacier immediately prior to that calving event taking place. And we know from the photographs that we're collecting every hour that there have been at least 4 of these very large calving events since we deployed last July. So this is going to give us an unprecedented insight into the processes happening at a calving surface. And I think I'll just finish it there.
Is our guest speaker here? He was here. Are you here? I don't know. He's about to be introduced. All right. We come now to the David Clayton Smith lecture, which will be delivered today by Richard Judd, who is the McBride Professor of History here in the History Department at the University of Maine and was a longtime colleague of Dave Smith. Professor Richard Judd's primary field of interest is U.S. environmental history, particularly in New England. He received his PhD from the University of California, Irvine in 1979 and first came to Maine in 1980 as a postdoctoral fellow. He returned to California in 1981 and worked for the next 3 years as the assistant and then associate editor for the Journal of Forest History, later merged with Environmental History. Since rejoining the History Department in 1984, Dr. Judd has taught a series of courses concentrated in 19th and 20th century America, including urban history, economic industrial history, environmental history, and Maine history. At the graduate level, he leads seminars in U.S. history since 1865 and in U.S. environmental history. He also edits the Maine Historical Society's quarterly journal, Maine History, and in conjunction with its publication, offers a graduate practicum in editing and producing a historical journal. Dick, the floor is yours. And one of these buttons, this one should advance your slides.
This one right here. Can't tell you how pleased I am to be delivering the David Clayton Smith lecture. Dave, as Dan said, this person who hired me initially when I came here, well, those 30-some years ago, and shepherded my interest in forest history since that time. And I think he'd be very pleased today to have me talking about 2 of his favorite of the thousands of topics that he was interested in, 2 of his favorites, farming and climate. So I'd like to talk about the so-called year without a summer, or what I've called here the Tambora summer, both historically and allegorically. I want to talk about it historically just for a few minutes, and I'm sure all of those of you who are in climate change research are very familiar with this anyway. But I want to look at it allegorically as well, as something that was embedded very deeply in New England conscience, in New England folk memory and things like that, largely because 1816 was also precipitated another disaster, not only an agricultural disaster, but also a kind of a demographic disaster, which began about 1820. That is the migration of people outside of New England and on into the Ohio Valley and the Great Plains area. So this has become very much a signature of New England agricultural history in the sense that it marks this period in which there's a massive migration out of the state. So let me begin just by pointing out a few things about the 1816 year. 1816 was precipitated, of course, by the eruption of Mount Tambora in the Java Sea, which sent ash around the world, and there was a global drop in temperatures, but it seemed to have affected New England more perhaps than in most places, at least in the United States and in Canada, very disastrous in Europe as well, because of the drop in temperatures that precipitated here. The temperatures began changing in April, sometime in April 1816, became a matter of concern at that point, and it reached what one historian called the wintry apex on July 6, 1816, when a kind of a rogue snowstorm swept through the area, coming down from Canada, leaving birds frozen in their nests and shorn sheep, sheared sheep, I guess you call them, dead, lying in the snow, about 18 inches in some places in northern New England, 18 inches of snow. And this is, again, July 6th. The weather did not improve much over the rest of July, and crops were affected accordingly. The grain crops, particularly wheat and the hay crop, both failed disastrously with some severe consequences for both people and livestock. Potatoes did all right during that year, but in September they had to be dug out of the ground with pickaxes and crowbars. But you could have potatoes. The Tambora summer destroyed the New England hay and wheat and corn crops, but it's important to remember that this is a very resilient culture, New England culture, and people reacted in different ways to it. On one hand, it's a very depressing thing to watch from the farmhouse window in 1816 as the snow piles up outside the door. People blamed this on icebergs in the North Atlantic. They blamed it on what one person called a deficiency of solar heat. It could have been caused by sunspots, some thought. But the big question was, were these causes going to exist in the future or not? That is, was this the new normal for New England, 1816? People figured that, well, if that's the case, well, our crops will adjust, plants will adjust, and it'll be all right. But other people said, well, if that happens, they'll have to readjust if the climate goes back to what was normal before 1816. So it's a big controversy about what was going to happen in New England after that period. And this was all the more depressing because people for about 50 years had been hearing from their own agriculturalists that as they cleared the forest, as they got rid of the trees in New England, the climate was going to get warmer. And this is Rudolphus Dickinson writing in 1813, just a couple years before the 1816 event. And he says, great changes of climate have always attended the cultivation of the earth. History furnishes abundant proofs that they have taken place on the eastern continent. The progress has uniformly been from a colder to a milder climate. As you clear away the trees, the climate simply becomes that much warmer. So the event of 1816 then was all the more depressing because it seemed to violate this notion, this optimistic notion that New England was going to become more Mediterranean over the years. So this is the event then that touched off one of the great migrations. There was talk during 1816 of what one person called a low nervous fever that seemed to sweep through the region, paralyze people actually is kind of an emotional reaction to 1816, this low nervous fever. And sort of the corollary to that was what we have come to call Ohio fever. That is packing up and moving out and going to Ohio. Now, what happened during these years is a whole series of events. The Treaty of Greenville, for instance, 1796, ended Indian resistance in the Ohio Valley. There's a trade embargo against trading with Great Britain and France in 1807 as we lead up to the War of 1812. This prostrates trade in New England. The War of 1812, the British blockade the coast and agriculture goes down again. And all this caused what newspapers were calling a kind of a melancholy despondency in New England itself. And then this is followed by the Tambora summer, 1816, 1817. And if that wasn't bad enough, in 1817, 1819, as crops began to revive as a result of all those people moving out to the west, there's a huge financial panic because of over-speculation in western lands, and the prices of grain drop again. And by 1819 then, what we find is that New England people simply have had enough. And they pack up and they move. The diaspora, the so-called Yankee diaspora, was really something unprecedented. People in the Allegheny Gaps, going over the mountains of the Alleghenies, talk about 100, 150, 200, 250 wagons passing through their towns on a weekly basis. None of them really knowing where they're going, people in these wagons, but they all knew where they were coming from. They were there to get away. I'm going to the west, they say. And that's pack up and leave. So there's this long diaspora that continues from about 1820 on through the 1830s and 1840s by people talking about we are bound to the westward. Now, this 1816 or 1807 or so, 1820 period has been crystallized in a theme that has really dogged New England agricultural history ever since. And this was sort of crystallized in a poem. I'm sure you can't read that here, but this poem begins, "How sad New England is the truth, that thy support and pride the youth, and even the aged men forsooth, forsake thee for Ohio." And then every refrain ends with that, "and travel to Ohio." And this is the feeling that people, all Americans, had about New England from this point on, is the place to leave, if you're farmer at least. And this is kind of crystallized in a book published in 1936 by Harold Fisher Wilson called The Hill Country of Northern New England. It's a major tome on everything you can think of about agriculture in the upland areas of New England along the Appalachian spine out there. And what Wilson does is characterize this whole region period from about 1816 on as what he calls New England's long summer. And he sees this event, 1816, as being the precipitating event that encourages outward migration, westward migration. The Erie Canal contributes to this, bringing western produce into the eastern cities. The gold rush in 1848. The Homestead Act in 1862, which gives free land to anyone who wants to move out to the Great Plains. All these together then sort of crystallizing this notion that New England, for farmers at least, is a place to get away from, a place you want to leave. What Wilson says eventually is that by 1830s, this is after all these events, the buoyancy of life in the uplands had worn away, the uplands of New England had worn away. The stimulus coming from the opportunity of exploiting new lands had departed, and the New England hill country found itself on the threshold of another epoch, and this is the beginning then of the so-called long winter of New England. And this point that New England is an agriculturally marginal area has been further dramatized by the signature feature that we think of when we think of New England outmigration, that is these stone walls then running through forests of old growth trees, signifying that once this was an agricultural region. Or another sort of signature characteristic of this is the dramatic reforestation of New England in the period between, say, 1840 or 1850 and on into the present here. These are the same places. You see this house here, this house here. Those are the types of things that we think of when we think of New England agriculture. Now, this in turn has been further interpreted in two very important environmental histories of New England. First of all, William Cronin's Changes in the Land, published in 1983, and Carolyn Merchant's Ecological Revolutions, which is also about the decline of New England agriculture, published in 1989. And their take on New England is that in the colonial period, settlers moved into this country, more or less raped the land, and with the soil's fertility declining, the rivers silted up, the climate changing, they simply packed up, went out to the west, kind of like the Okies in the Dust Bowl during the 1930s, packed up and went out to the west and started this process all over again. So it's a story then of what Cronin and Merchant call environmental degradation, sort of a downward spiral in the environmental integrity of this particular region. So historians have accepted then Wilson's Long Winter as a story, a cautionary tale, if you will, of the prospects for New England farming in this area. So let me kind of rewrite this history very briefly and begin with two anecdotes about how people survived 1816. And then from there, I'll talk a little bit about what I think New England agriculture is all about. In 1816, the people in Garland, Maine, which is not too far from here, found that their corn crop had failed and their wheat crop had failed, and they faced starvation. But at the very same time, in the town next door, this huge flock of passenger pigeons moved into the trees. So they set to work turning their flax, which they grew, into nets like these. The birds came into the nest. They captured tons of these birds. And in this atmosphere, they had enough to eat. They had enough to feed their pigs. They did fairly well. And then the next year, rather than grow corn, they decided to grow clover, took the seed, sold it in Bangor, and made a pretty good profit. Other people that were near major rivers like the Androscoggin or the Connecticut would, rather than grow crops, they would go down and fish, set nets like these across the rivers, and capture salmon and shad, and live fairly well in that sense too. So if the Yankee diaspora was not then an act of desperation, you might say, I mean, if these people were managing to adapt in different ways, how then should we really view this outmigration? If it's not then an act of total desperation, what exactly was going on here in New England to send all those people out to the West? And this is where kind of a revisionist history comes into play in the period after, say, 1820 or so. Is this indeed a cautionary tale, how we should treat the land better so we don't have to move first to Oklahoma and then from Oklahoma out to California during the Dust Bowl? Or is there something else going on here in New England during these years? I would like to suggest, and several historians have done this, that outmigration is nothing peculiar to New England during these years. This is a national phenomenon. What we're seeing is people from all over the East, from here to Ohio to Illinois, moving from rural areas into cities. So it's a part of the industrialization and urbanization process itself. Places that had lots better soil than New England were also experiencing outmigration at a much more dramatic rate, actually, than in New England. It's also a trend based on declines, long secular declines in grain prices, because we're opening up new lands, not only in the American West, but in Canada, in Australia, in the Russian steppes. All these are driving grain prices down, so people are moving out. It also reflects a change in labor demands. As we're moving from hand threshing like this to machines, sons and daughters just aren't as necessary as they used to be, so they're moving out to new places. I would say the third thing that's happening in New England is that there is a dramatic outmigration from Wilson's Hill Country, but in fact, this is land that probably never would have been settled had there been land out west available to them before 1790 or so. In other words, Maine was the place to go before 1790 if you needed more land. You could hop on a coasting steamer or a coasting ship, sailing ship, come up to Maine virtually free, pick up free land. It was just the place to go. So once those lands out west opened up, what we see is draining. This drains the people from lands that never really should have been settled in the first place. So this realignment, this winnowing of the hill country population really kind of expresses the strengths as opposed to the weaknesses of New England agriculture during these years. So what happens to people who stay behind then? Hal Barron, for instance, who's an agricultural historian, has done an interesting study on what he calls those who stayed behind. The people not who went out west, but the ones who stayed here. And what he finds is that they're doing very well here in New England. What happens, the people who left were largely propertyless, poor farmers, or artisans whose skills were no longer necessary. The people who stayed behind consolidated these abandoned farmlands, the shops and the mills, brought them together under one family. They passed these assets then on to their children, and these children intermarried, and these kind of mechanisms for persistence then gave rise to a very stable and very rich community life in these towns that were supposedly, according to Wilson at least, abandoned communities. They embedded themselves in place through their kind of very rich cultural life. The Grand Order, the Grand Army of the Republic meetings, the Grange meetings, fraternal orders, sports clubs, things like this. Very rich community life. Baron finds going on here, which helps again to embed these people in place, giving them a very strong sense of persistence and loyalty to the land, you might say. So there's not really a crisis in terms of the communities, although they are shrinking quite a bit. So that's what's going on here in part. The other thing, and this is sort of the surprising element of this, is that what we see in agriculture in New England is a very rich and diverse development from about 1860, 1820 on. Surprisingly, fertilizer costs per acre in New England are lower than in any place else in the country. And that's, people are talking about soil exhaustion and things like that. And at the same time, the value of the product, because these farm communities are very close to metropolitan areas, the value of the product per acre is higher than any place else in the country. They're experiencing increasing yields per acre, more than any place else in the country as well. They have the highest farm savings rates of any place in the country. So what's happening here is there's a consolidation of farming into the hands of these fairly prosperous farmers and a movement into specialized crops, dairy, tobacco, garden crops, sweet corn, orchard crops, blueberries, cranberries, things like this. And long and short of it is New England farmers after 1820 were surprisingly prepared for modernity as we move into the second half of the 19th century then. Farm specialization includes finding market niches where they can compete with Western produce coming in, the development of agricultural colleges, community fairs, boards of agriculture, things like this, to promote specialization and commercialization and new techniques. New manures, guano being used during these years, new fertilizers, and as I said earlier, labor-saving horse-drawn equipment. So at the end of this period, this long winter, as Wilson calls it, in the 1870s, 1880s, New England is surprisingly well positioned as an agricultural region, despite all that talk about outmigration and unpredictable weather and such. But that sort of begs the question about what's happening in the hill country. This is what I was talking about so far, is really the lowlands, the river valleys, places where soils are rich and agriculture can proceed with fairly good market infrastructure. The highlands, or the hill country, which Wilson talks about, is really the epicenter of that outmigration. This is where Wilson really concentrated his analysis on the outmigration from the long winter of New England. And here the story is more complicated, you might say, but it's still one of adaptation rather than environmental degradation. What we see happening in northern New England in places like this is a persistence of what we have called mixed husbandry or mixed agriculture, that is growing as many crops as you possibly could on your farm to hedge against the failure of any one particular crop. And this is a quote from a farm journal of the time, and it sort of explains the strategy there. Persistence of mixed farming is not unusually safe. It is not usually safe to venture all in one specialty. The owners of the average hill farm should aim to supply their own necessities, their own subsistence as far as practical, and for the surplus raise that which will bring the most for the least expense and not impoverish the farm. So grow as much as you can on each farm, and in the long run, you'll find something to eat and something to sell out of this combination of crops. This is not something unique to New England. Mixed farming, you find it all over the world, but it's become proverbial here. It's something that we identify New England farming with during these years. And environmentally, this region is very well suited for that. This is a sort of rendition of the Hill Country Farm. As you can see, it's a very complicated landscape which involves different hydrologies and different soil types across the just within the farm itself. And the idea of those hill country farms, the way they adapted, was to find something that they could draw out of every single foot of this varied landscape here. Farms, flat land for fields, hillsides for meadows, stony land for orchards and wood crops, et cetera, so that you've got something coming out of each of these particular parcels on the farm itself. This is the kind of adaptation then that you see after 1820 or so that makes persistence on these hill country farms possible. So I sum up with a quote from Senator George Aiken of Vermont, who came from the hill country of Vermont and was a special proponent of this persistence in the hill country itself. He's talking really, despite Wilson's lone winter, he says, they remained not because they lacked the ambition to move west, but because they savored the, quote, freedom of thought and action inherent in this rugged landscape. The New England farmer, I say, came to terms with the land itself during these years. So just to summarize, outmigration has encouraged the impression that the New England countryside was insular and stagnant, but in fact it was well fortified to endure the, quote, melancholy despondency of 1816, 1820. Families discovered no crop profitable as Midwestern wheat or corn, but they grew it, as they grew acquainted with their land, they found ways to extract profit from particular assemblage of soil type, slope aspect, microclimate, and hydrology available to them. Through trial and error, New Englanders sustained themselves in their environment, offsetting the drain in fertility by light cropping, rotation, manuring, and forest fallowing. Out of the ruins of 1816, 1820, they achieved a new equilibrium with the land, and this served them well, at least until the 20th century, I would say. The year 1816 was inscribed in rural memory, but not in rural fact. Thank you.
Dick, what did the long winter do to the fishing villages of Jonesport and Eastport and Lubec and Gloucester? What happened to those populations?
Well, the complication is that this is the sardine industry was picking up during these years too. The late 1880s and 1890s, we began to see sardine canning. So the outlying farms really had something to fall back on. It's marginal country, as you know, for farming. But people could send their wives and their kids into the sardine factories when the ships came in. They would work there. So it's a very complicated economy that's developing during these years. I would say farming is just sort of on the margins of the way they really make money during these periods.
He was asking about Tambora itself, how it affected those coastal towns.
Oh, I'm sorry.
I was wondering I remember Dave Smith saying, if you really look at the outmigration from the Machias region, it was considerable, but from the adjacent fishing areas of Jonesport, it was far less.
Right.
And I was wondering if that's true. That was a casual comment that he made. And I wondered if the fishing communities that didn't in any way hardly depend on agriculture, did they remain stable or did they grow?
My guess is they actually probably grew with the sardine. Well, the lobster industry is migrating up into there by the 1880s as well. So there's another form of stable income so between lobster and sardines. Sardine industry is a big deal. I mean, it is, and global markets, Maine sardines are right at the top of the list. So I would think that I have seen charts of where the cold weather really, where the weather was coldest, and it sort of extends up along the coast, from southern New England, which is all cold, and then it sort of moves in a kind of an arc up along the coast. So it was probably colder on the coast than anyplace else, if that answers anything.
Thank you.
Yes.
Is there any relationship between changing in farming and the rise of the lumbering industry?
Farming, yeah, has always sustained the lumbering industry up until 1950s or so, when lumbering or pulp and paper production becomes more mechanized. Woods operations become more mechanized, but farming was the source of labor for the lumber industry traditionally, always has been, and it was a source of income for farmers during the winter. You know, you can't really harvest any crops between, say, October and midsummer or so. So farming, in fact, it's a system we've come to call agroforestry, which is this union of these two economies in a way that they become almost inseparable. You can't have farming without, in northern New England, you can't have farming without forestry, you can't have forestry without farms. So, you know, it's very much tied together. Commercial farming sort of separates the two in the late 19th century, but even still, it lingers on up until you start to see skidders and chainsaws and things like that in the woods. Yes?
I think I'm particularly interested in this kind of period when they're kind of trying to figure out what's going on. Because a lot of people are trying to figure that out with climate change now. And I mean, they're kind of saying that it may be icebergs, might be kind of solar fluctuation, might be great winged beasties.
Earthquakes too, for some reason.
But I had two questions about this. Kind of, was there no kind of idea that this was the result of moral infractions or some kind of religious infractions, that they offended God or anything? And just another kind of question with that is, when would news of Tambora have permeated into Maine? And at what point, I have no idea about this, at what point would the connection between Tambora and what had happened actually kind of begin to take root?
Yeah, I wish I could answer that. I've never really traced it that far forward. I don't really know.
Didn't Ben Franklin identify it when he's in France?
He did. He did everything. Yeah, that makes sense.
Ben Franklin was dead.
What was your first question?
I was whether
Lockheed was Franklin.
Yeah. I'm sure there were. I haven't really looked into them, but there's a whole series of what we call Jeremiah's sermons that use natural disasters as a way of pointing out, moral decline, I guess. And I'm sure this would have been among them. I didn't really look into that, but that really reaches a peak in the late colonial period. But there's still a lot of residual Puritanism in New England at that time. So I'm sure, yeah, that was brought up. I'm sure it was.
Is it true that Ohio Street and Vanguard, that heads off to the west, was the funnel?
Dave said so.
I mean, you really think about this, it does go in that direction.
Sure.
And it's called Ohio Street for some strange reason.
There aren't any other state named streets. It's just Ohio.
That's what Dave always said.
There's no other state named streets.
And it heads west, not east.
Oh, yeah.
Well, sure, head southwest.
Regarding the allegorical matter, do you think there's any similarities to where Maine agriculture is today? Going through generations of decreasing numbers of farms, we're suddenly watching an increase and a change in the national and the local agricultural state. And as someone who is actively farming in Maine, I'm interested to see that there is this concept of a positive look. Sounds similar in some ways to what you're describing in 1860.
Right, yeah. The 20th century has been really hard on Maine, especially after World War II, because of the interstate highway system and refrigerated trucking, the big dams on, Colorado and the Columbia and the Snake River. All this opened up enormous acreage out west. And of course, now all this can be trucked east almost overnight by these big trucks. So I would see the real decline in Maine agriculture coming not so much in this period that Wilson talks about, but in the post-war World War II period. So this turnaround has been fairly recent, I think since the 70s, mid 70s or so.
Didn't the reforestation start earlier than that?
Yeah, well, see what happened is that in about 1830, we get what's called a sheep mania. That is, everybody wants to produce wool. So all that land that had been left for woodlot gets cleared away. There's a remarkable deforestation from about 1830 through the end of the sheep mania, which is mid-1840s or so. And then the forests start to come back after that, because what they're doing is they're going into dairy farming and importing Western grains. And if you import Western grains, you don't need to grow your own grain. So all that stuff that had been cleared for sheep pasture now starts growing back. So you really see that from, I would say, about mid-1840s or so on into recently, that reforestation. So now you have 90% of Maine's forested, which is remarkable.
Thank you very much. All right. We come to the final official acts of the 2016 Warren Symposium. First, I'd like to thank all of the presenters, both oral and poster, for excellent jobs. This has been an outstandingly good symposium. Fascinating presentations. What a great variety of work going on in the Institute. We know it, but it's at this event that we get to see it and share it. And I hope this too will lead to many new collaborations now that you know what everybody's doing. All right. At this point, we're going to do the awards. We have several categories. I am going to start with the oral presentation awards. I'll begin with third place. Can somebody give me a drum roll? And it goes to Samuel L. Belknap III. The second place, drum roll, goes to Issei Tanaka. And now we need the really big drum roll, everybody in the room. First place for the best student presentation goes to Benjamin W. Parton. We have one award in the poster category. First and only place goes to Carl Tuga. Next is the Churchill Award for Outstanding Exploration, given to one of the graduate students who spoke on their work that was funded by a Churchill Award. And this one goes to Kit Hamley. We also have an honorary Churchill Award to one of the undergraduates who presented a poster, and this goes to Marissa Bovey. I guess we should advertise better that people are actually possibly going to get awards. We have one final award. Each year we give out an outstanding service award to one of our students, and this too goes to Kit Hamlin. All right. What is left now is, first, before I thank people, I'd like to remind you that we are going to have a group photo and also keynote speaker photos immediately following this and before you get to eat. So I suspect that going outside might be the best. There's not really room up here, so we'll go outside for that photo, then we'll come back to eat. I want to thank all of the CCI graduate students who participated in moderating sessions, as well as those who assisted with the event setup and who will help us with cleanup activities. You know who you are. Special thanks to Nora Theodore for taking photographs at the Bourne Symposium. Thank you. Thanks to Andrei Kurbatov, Mark Royer, and Amy Coretta for their assistance with the audiovisual component for this event. And of course, although I get to stand up here in front of you, we know who does the real work of making this happen. It's Betty Lee and Becky Adesi, and they deserve a great round of applause.